Yeah, so for the broad audience, complex organic molecules, which are essentially carbon-based molecules containing 6 or more atoms, are simply fascinating because at least some of them are considered to be direct precursors, so fundamental building blocks for life as we know it on Earth. So when we detect molecules such as glycolamide, which is an isomer of glycine, the simplest amino acid, we are basically constraining what is the chemical inventory that was available before planets even form. And the presence of these kind of molecules shows us that the chemistry leading to more complex key prebiotic species such as amino acids, nucleobases, but even sugars, phospholipids begins very, very early in the star formation cycle. And potentially this material could have been inherited, delivered to early Earth through the impact of comet, asteroid, meteorites, and so on. And also regarding the other elements, so in this case, sulfur, it's a key element for life that is present in all major types of biomolecules, highlighting probably its role in the folding activity of proteins. But yet the chemistry of sulfur is not fully understood, the interstellar chemistry of sulfur. And one particularly relevant example in this context was probably the detection of dimethyl sulfide in the DMS, because these molecules are not only relevant from a prebiotic point of view, but also in the search for life elsewhere in space. There was some news because DMS was considered until quite recently as a unique or robust biomarker in the search for extraterrestrial life elsewhere. But we detected this particular molecule in, let's say, in the inert interstellar medium, suggesting that we cannot consider this molecule anymore as a biomarker, or at least a unique biomarker, because it can essentially form abiotically and quite efficiently in space. Yeah, so the thing is, a star formation can essentially be seen as a chemical journey. So it begins in cold, dark molecular clouds, where very simple molecules such as CO freeze out on the surface of interstellar dust grains, and then it slowly builds up let's say the chemical complexity, mainly through surface reactions and also with some help from additional gas phase routes. But the problem is that there is a current gap in our knowledge regarding what is the chemical inventory that is found in these very, very earliest stages of star formation in this molecular cloud, and the rich reservoir of key prebiotic species that had also been discovered in the minor bodies of our solar system, such as asteroids, comets, and meteorites, which includes a wide array of key prebiotic molecules, many amino acids, nucleobases, and so on. So we are trying to address this gap by tracing the chemistry throughout all this star formation cycle. And in particular, well, my work is focused on these very earliest stages, so in molecular clouds, in particular in one molecular cloud, one shocked molecular cloud that is located in the center of our galaxy, in the center of the Milky Way. So it's a shocked environment that essentially help us or it provides us a snapshot on the chemistry that is occurring on the surface of these interstellar grains, because due to the action of shocks, the grain mantles are essentially released into the gas. So the beautiful point here is that many of the molecules that we detect in space have not been discovered so far. So these are first detections, the work that we do, and also the work that many colleagues in the field do. So each single detection really expands our understanding on what the chemistry looks like, how complex can it be, and also, and more importantly, what are really the raw materials that planets could potentially inherit throughout this star formation cycle. Yeah, so I really believe that this interdisciplinarity is one of the key aspects. So it's really the core of what makes our approach and also the approach of other groups in the field so powerful, because we mainly detect molecules using their rotational fingerprints. So the specific frequencies at which every single molecule emits radiation. To do so, we use radio telescopes. But of course, in order to know what are we looking for, what are these frequencies, we first need to characterize the molecule in the laboratory. So we need to get this molecular fingerprint, we need to characterize, to measure the rotational spectra of each particular species of each molecule in the laboratory. And then we have in parallel quantum chemical calculations that help us with, let's say, they play a crucial bridging role, because first it helps us to guide these laboratory searches, but also it allows us to rationalize how the molecules are formed or destroyed in ISM conditions by using mainly astrochemical modeling. Interestingly, this cycle is sort of iterative. So every time we detect a new molecule, we typically want to go back to the lab to expand a little bit the spectroscopy, to characterize even further these species, and in some cases also study related molecules. And then with new theoretical work, it often provides new candidates for future interstellar detection. So it's a really, really nice interplay between the different pillars of the field. So, I would say that ALMA has been transformative for the field of astrochemistry in general, because it has a superb sensitivity and spatial resolution, and this allows us to basically map the distribution of molecules across different sort of environments. Nevertheless, much of our work toward these galactic center clouds relies on single dish observations, so observations using single dish antenna, which have recently added broadband receivers to their tools. So one example is, for instance, the ultra broadband receiver that has been installed in the Jebes 40-meter radio telescope, one antenna that is located in Spain. So basically, it allows us to cover at once the whole Q-band, so between 30 and 50 gigas, and this helps a lot with all these new detections. And probably one of the most exciting discoveries for me personally would be the detection of a sulfur-bearing cycle, so a 6-member sulfur-bearing ring that we detected recently this year, that appeared in Nature Astronomy. That is the largest sulfur-bearing molecule that has been found so far in the interstellar medium, and also a beautiful connection between the chemistry of these very early stages of star formation, these molecular clouds, and the rich content of sulfur-bearing species that have been found in the minor bodies. And also it highlights how really harmonized laboratory, theoretical, and observational work can help us to really push a little bit the frontiers of chemical complexity in the interstellar medium. Yeah, so thanks a lot, William. So the Miller Prize is really a great honor, especially coming from a community that I would say that I deeply admire. And also, I think that ISMS is probably the home conference for people who work in the interface between spectroscopy and also astrochemistry. So, given the possibility of give a talk there is really something that I'm generally excited about. And in my talk, I'll try to take the audience on a chemical journey toward the limits of chemical complexity. So I'll quickly present what is really the strategy behind some of these new discoveries, some of these new detections, how we do combine the laboratory work with this theory, with the observational tools. and then walk through some of the latest discoveries, so some particular detections, and explain what they tell us. So what are basically their implications in the context of interstellar chemistry. So, I mean, to me personally, I think that ISMS is one of the most even intellectually stimulating conferences that I regularly attend. So I think probably the key to maximize our time there is to be actively present in the different discussions. So don't be afraid to ask any type of questions, nor to be involved in the conversations that also happen around the conference during coffee breaks, during lunch, dinners, and so on. Because to me, I would say that some of the most productive collaborations have even started in some of these interactions. And probably my specific advice for young researchers would be to first do your homework before you arrive to the conference. So try to map what are the sessions that you are more interested in. Even try to also attend some sessions that are even outside your specific field of research. Also, probably I would say that don't be shy or don't be afraid of really introducing yourself to people, especially to speakers whose work you truly admire, because in general, most of the people in this conference is, I would say, deeply happy to talk in general. And finally, if you are presenting a talk there, I suggest that you really invest some time preparing your talk, preparing your slides, your presentation, because ISMS in general has a really good tradition of nice talks, of nice presentation, and you could even apply to some prizes if you are a student. So, for instance, the Snyder Prize if you are doing astrochemistry. So that would be probably my advices for young people.